only read, as you can see right over there. Obvious, because when you input the characters, it goes through a stream, as I said there. It's a stream of characters, to bit streams. And bit streams will, everything will come in the form of a bit stream, and that's why we need the controller to convert them into byte blocks. So now, if you look at the next one, the reason we need it is the controllers. The controllers, all of them, all the devices must have their own controllers. And the controllers literally help convert the serial bit stream into block bytes. Serial bit streams into block byte. So that is essentially what they're doing. Okay. It's a chip and takes the form of a chip on the parent board or a printed circuit board and insert it into the expansion slot. So it is basically a chip. That means a hardware. And that's why we are here talking about it. The one common thing is what's the difference between this controller and the driver. Or the driver, we are familiar with this word driver. But remember, driver is a software. And a software that comes from a third-party hardware vendor. I must say third-party hardware vendor. That means it's not given by Microsoft. It's given to you probably by HP because you are using HP printer. Okay. So if you are using HP printer, you download the printer driver for their printer from HP's website. So HP gives you the software, not the operating system provider or Microsoft. So essentially, there's a potential source of conflict there. So the line that they have mentioned, the thing that they have mentioned right here, the device driver is just a code inside the OS. I need to explain this thing a little bit because it sounds like as if they come packed together. No, that's not the way they come. They differently come from two different sources. But after installation of the driver, those codes must sync in properly into their compatible operating system so that when it comes to doing something, they do behave as if they belong to each other. Okay, they are part of these codes, the driver codes are part of OS, but they are not. But they sync into the kernel, at the bottom layer of the kernel. So there are quite a few restrictions there as well, because they are third-party codes, so they're not allowed to give system calls or handle any system calls. So there are quite a few restrictions, but still they behave together. They work together. All these controllers, which are hardware, they are connected to CPUs through bus, and this bus will play an important role in data transmission. Each device controller, which is an electronic component inside the computer, is in charge of specific type of devices. Any device connected to the computer is connected by a plug-in socket. The socket is connected to a device controller. Okay, and that's how it all works. Device controller, this is a very interesting thing, and you should try to remember. Device controller works as an intermediary between, in fact, you can just put it in a simple way, that is your keyboard, for example, and here's your keyboard controller, here's the driver, keyboard driver, and finally here is your operating system. So as we understand first that these two are software, these two are hardware. Okay? So naturally, this one works as an intermediary between the hardware, one hardware, and one software. The controller. Its prime job is to convert the bit streams into byte blocks and store the byte blocks in a buffer. And that's true. All of them, they have a buffer. All the controllers have two parts. One that does the conversion, and the other part is the buffer. Well, after conversion, those byte blocks or those input signals will be stored in the form of byte blocks. This is buffer. Okay. And the driver right here in our picture works as an interface between the controller and the operating system. Okay, so that is the general idea and general structure. We must remember, we shouldn't get confused. Finally, we are here, memory mapped I/O. What does it mean? Well, the simplest way of understanding I/O is, as I said in the previous slide, that this is your device. This is your device. And you use the device to give an input. The input must go to a chip that is called the controller. And the controller has a buffer. The controller will first do the conversion from bit streams to byte blocks, and those byte blocks are now stored right here temporarily, which is the buffer, the controller buffer. Now the question is, their final destination eventually, because I mean, just being in the controller buffer doesn't mean that your inputs have been accepted. Well, in the first place, the reason you made those inputs was that you didn't want your inputs to go anywhere and everywhere, but you wanted these inputs to be part of a process. Think about that. You want them to be placed somewhere in the appropriate place in RAM where process is running and process is probably waiting to have those inputs from you. Right. So its final destination is on RAM at a particular specific position on RAM where they are required. Now, how will you do that? How will you do the transfer? Well, there's also another part of the question, another part of this transaction. That is that how will the CPU know? How will your machine know that you have actually used the device? You clicked the mouse or pressed the key. So that is the second question that we'll raise. The first question is, who will be responsible to transfer the data? Well, as we expect, it is CPU. Okay. But then again, the second question comes up, how will the CPU know? Because CPU is always busy doing a whole bunch of things, important. Then how will the CPU know that you have actually pressed a key or clicked the mouse? Only then the CPU can switch to action, because it's IO-related actions. So the whole point is that we have the buffer, and the CPU will have to use the system bus, okay, to transfer them somehow, to arrange to transfer them to the RAM, the appropriate position of RAM. Now that they do by using a technique that is called memory mapped I/O. There are two versions of memory mapped I/O, and the second one being most popular. There's also a third version that will basically combine the first one, the third one, the first one, the second one. So let's take a look at the first one. Well, to start with, the first thing that the CPU will do is to assign a port number to all these controller buffers. They will have a port number for all these I/O buffers, the controller buffers. So these port numbers, they have assigned a port number, and these port numbers will be addressed by CPU. What CPU will basically do, CPU will use the system bus, which basically comprises, as you know, of 3 buses. That's altogether collectively we call them system bus. One is data bus, one is address bus, and one is control bus. So they use the bus to read from these buffers and put them in its own reg. So reg is a register. So all the registers that we have of all the registers that we have inside CPU, we have another special regs that's for I/O ports, and it will be stored right there inside the CPU. And then whenever that piece of data is required, it will be transferred from that. So it will go from there, from the register, it will be placed wherever it wants to go on RAM. Okay, wherever it wants to go on RAM. So that is what it will do. Okay. That is the first way of doing it. So basically read it and write it. So everything on the buffer, the controller buffer, will be read into a register, and from the register, the things will be written into the output controller buffers, like buffers of the output devices. So that's the way the first approach works. The second approach is more efficient because the first approach we needed two transfers, right? The first to the register, and from register again back to the RAM. But the second one is much more easier and convenient for CPU to do it, because CPU wants to keep them straight on RAM. Because it's for the PC, it's much easier to move on the RAM because that is what it is doing. So wait for another transfer from register to that means an extra bus cycle. An extra unnecessary bus cycle needs to be spent. Okay, so that will create a problem. So here, don't have to worry for that extra bus cycle to transfer them from the register into the RAM. It can easily read it from the RAM. So for that, what we do, and of course we have the I/O ports, and all these I/O ports have a dedicated address, okay, have dedicated and unique memory address. So everyone knows, even PC knows, where should it go when it comes to reading, and input, a keyboard input, because it has its own address space, and it is always unique and it's always dedicated. It's a kind of fixed location. And these two are separate, as we say, the unique. This is for the process, and this is for the I/O. So the PC doesn't have to, we don't have to use the bus two times, because it's better not to, because bus is used for several reasons. Okay, and bus is a lot of other important interactions to do, because if you use an extra bus cycle, that means you are basically wasting a little bit of time. So rather than using the bus cycle, it is written directly into those address spaces. Okay, at the top of the address space, there is a part that is always defined for the I/O, and the I/Os will always go there for each port. And from that port, the PC can easily fetch the data or read the data whenever it has to. So that is the scheme for I/O, memory mapped I/O, that is used to transfer the data. Here's how it works. CPU wants to read a word either from memory or from the I/O port. It puts the address it needs on bus address line, and then asserts a read signal on a bus control line. A second signal line is used to tell whether I/O space or memory space is needed. If it is memory space, the memory responds to the request. If it is I/O space, the I/O device responds to the request. If there's only memory space, every memory module and every I/O device compares the address lines, the range of addresses that each services. If the address falls in its range, then it responds to the request. Since no address is ever assigned to both memory and the I/O device, there is no ambiguity and no conflict. That is exactly how it happens. And that's why we give them a dedicated place and a unique memory address usually on the top of the address space. There are advantages and there are disadvantages. One of the disadvantages is the need to figure out at boot time which memory addresses are not really memory addresses and should be considered the I/O port addresses. The direct that brings us that means the direct memory access. That brings us to direct memory access. Now, usually we say the interrupt driven I/O is the best I/O. The direct memory access at DMA. Now, traditionally, as we always say, that the best I/O is known to be interrupt. This is a traditional approach. Interrupt driven. That means we use interrupts to alert the CPU. We'll talk about it later. Remember, I raised the second question. How in the first place will CPU get to know that you have pressed a key? Only then CPU will switch to action, do the memory mapped I/O. But that part, to answer that part, we have no other choice, but we can't write any algorithm for that. We can't make any prediction. So we have to depend on interrupts, and that's what we do. So interrupt-driven memory mapped I/O. So interrupt-driven memory mapped I/O is supposed to be the best form of I/O management. We already know it, and we acknowledge that. Okay, because it's all controlled by CPU. Simply, when CPU is involved, then definitely everything must go well. But then why do we need DMA? DMA is a different technique. DMA, that direct memory access. Well, the root of the reason lies in the way that in the younger generation or in modern times, we use the computer. So if you give your computer to an elderly person in your house and ask them to use it, you will see how they use the computer. In fact, some of them still use one finger to type, and they will just carefully press the keys, and they will have time to find where exactly the keys are. And then they will spend probably the next 5 minutes reading from the screen what they have just typed in, and then they will start typing again. They're really typing. But if you compare that with the way you or your friends use the same computer, especially while playing an exciting game with their friends, you see they literally hammer on the keyboard with their 10 fingers. I see it. They literally hammer on them. Okay, and that's not all because they want to make it faster. They want to do it faster because it's all about competition, like who can kill the monsters faster, that sort of game, something like that. And not only the keyboard, he is clicking wildly on the mouse, and probably he has turned on to add more fun to it. He is already doing already engaged in a live chat through the webcam and mic. So think about how many different devices that he's actually using at the same point of time. At the same time, of course, he wants an immediate output. He wants to see that it is happening on the screen. So monitor is another output device. So think about it. At what breakneck speed is putting these streams of inputs from multiple devices into the system and getting the outputs. Now, if you still continue to work with interrupt-driven I/O, then your CPU will be completely engaged. The CPU will have nothing else to do other than taking care of the streams of inputs. So your overall machine performance will degrade, and in fact, it will slow down. It will become non-responsive, unresponsive. So that is why we needed a technique that can serve two things. Reduce the number of interrupts. First, reduce interrupts. The same thing that we did in clock, remember, by using soft timers. Also, the next thing is it must free up CPU. And number three, serve multiple devices or device controllers at the same point of time. Something that's capable of serving multiple device controllers at the same time. So these are the three priorities. But at the same time, we do agree that if they want to play the computer, they want to use the computer at a breakneck speed, well, let them do it. So we have to support them. Okay? Now, when computer was invented, definitely no one thought about it. The computer would be used for playing games. Definitely it wasn't invented for that purpose. But then eventually it evolved into something that is a part of entertainment today. Entertainment in so many different ways. It's someone's social life is there, someone's entertainment life is there. Okay, so it provides everything except food. Well, grab food, yeah. So everything. So naturally, we have to satisfy all these customer needs. There's a commercial interest in that as well. So naturally, we had to introduce this DMA. Remember, DMA itself is a technique. Okay, and this technique is implemented through a chip that is called DMA controller. Now, one of the most common questions that we ask is, you see, DMA controller is integrated into each device. The DMA controller has access to the system bus independent of the CPU. The DMA controller regulates transfer to multiple devices, often concurrently. DMA controller carries multiple registers. One of the popular questions we ask is how many registers there in a DMA controller. If you get this question, the answer, please remember, is at least 3. Minimum 3. Or 3 or more. Okay? Because it depends. The first, it will get a memory address register that is given to it by CPU during activation time when CPU activates it. Then it will have a byte count register that will help it to serve all the different. It's simply a counter that will be loaded and will decrement it with every run of the loop until it reaches 0. And then it will move on to serve another device controller. So that is exactly what this one is for. And finally, depending on how many, remember we say the multiple devices, how many controllers or how many devices is serving. For each device, it will have one register, one control register. Basically, that's an internal one that will store the information, store the values, how many registers are there and how many things it needs to clean up. So that is how many devices are there and how many devices, and how many data byte blocks pending in each of these devices. That number will be loaded on that counter register. Okay. And then it will be decremented gradually. So that is what they're going to do. How DMA works in general, and then we will see it in a more visual way. Let's give it a read. The CPU sets the DMA controller registers so DMA knows what to transfer where and how many transfer. The CPU commands the disk controller to read data from disk to its internal buffer, then verify the checksum. The DMA controller initiates the transfer by issuing a read request over the bus to the disk controller. The disk controller transfers a word or a byte from the internal buffers to main memory at the address that is described in the DMA's memory address register. The disk controller sends an acknowledgement signal to DMA controller when the write is complete. Simultaneously, the DMA controller decides which device to service next using the priority scheme. In each transfer, the DMA controller increments the memory address to use and decrements the byte count. Okay. If the byte count is still greater than 0, the steps 2 through 4 are repeated until the count reaches 0. If the byte equals to 0, the DMA controller interrupts the CPU to let it know that the transfer is now complete. So basically what it does, at the very beginning, let's look at the picture. An input happened. The moment an input happened, it will generate an interrupt. That is the first interrupt. And as the CPU gets the interrupt, this time CPU will not jump into action straight away. Rather than jumping into action, what it will do, it will program the DMA. It will tell everything, how many transfers it will have to do, and the byte controls and everything, and also it will give it how many devices need to be served, and one of the most important things, handing over the address register. Okay, so that is what the CPU will do. CPU will simply hand over the address register to DMA. Now DMA knows everything about memory, and the DMA also knows how many devices they're going to serve. So that number will be loaded on the counter. This is called the byte counter. And one counter for one device. So basically, for each device, and DMA will be instructed to read from the drive. So basically, read from the buffer. Okay. Basically, it will read each of them one by one from the buffer, clear? From the buffer. And as it reads from the buffer, it will hand over one of the address to the disk controller and ask the disk controller to transfer the data to the main memory. So one of the things the students confuse that I've seen over time is the actual transfer is not taking place from DMA. The actual transfer is still taking place from the disk controller buffer to memory. This is the actual data transfer. That's why we call it direct memory transfer. Okay, but DMA controls it. So DMA, as it gets the CPU instruction to read from the buffer, it will read from the buffer, and it will use the command. Okay, it will increment the memory space, and it will decrement the byte. So basically, it grabs a bunch of addresses, P addresses, and keeps distributing it freely to the disk controller. And the disk controller will get the bus to transfer the data into the main memory. So that is exactly how DMA works. If someone asks the question that which one is faster, is it DMA controller or DMA or memory mapped IO? Is DMA faster or the CPU faster? As you can see the answer here, the answer is always the CPU. But then why do we use it? It's because when the limiting factor is not the speed of the IO device, thing that I casually told you, it's all because the way we, the modern users, use the computer device. It's because of us that we need a new technology, and that is what we have in the form of DMA. Why does a controller need internal buffer? Because it uses the checksum for error checking, to ensure that all transfers have been done properly. Now, this is very important. DMA can operate in 3 different modes. Very, very important. They ask questions from here. Word at a time mode, you have to remember, block mode, and flyby mode. In word at a time mode, a cycle stealing may happen. What is cycle stealing? Because the device controller sneaks in and steals an occasional bus cycle from the CPU to transfer a word or a byte block. Block mode, that is the most common one, is also called the burst mode, when CPU switches to its IO bus, and this IO bus may continue over a long period of time. Okay, that is what we call the burst mode. To acquire the bus, issues a series of transfer, then release the bus. They're efficient because transfer multiple words. But there's a problem that if your bus is too long, then the machine, the CPU, is lying idle. CPU can't do it because CPU needs the bus. The bus, system bus, is always under the control of the CPU, and it's supposed to be. Finally, we have the flyby mode. The flyby mode, the DMA tells the device controller to transfer the data directly to main memory. To have the device controller send the word, the DMA controller, an extra bus cycle is provided for word transfer. So make sure you remember and you understand this part. Okay, because sometimes in the exam, in the questions, they will quote these words: cycle stealing. In which mode of DMA transfer cycle stealing occurs? In which mode of DMA transfer an extra bus cycle is provided for word transfer? These are the kind of questions. These 2 that I've marked, I can remember they're the most common ones that I've seen. But the questions can be made in that way. Okay. So please take special care of this slide. That brings us to interrupts. What is interrupt? An interrupt, as we say, is a way to knock CPU up, to let CPU know that someone has pressed the key. For interrupts, usually come from the controllers. And we have also an interrupt controller that comes from the device. This is a tiny electrical signal. But right here, in between the CPU and the interrupt controllers, we have a layer of codes that do everything. That is called interrupt handler codes. Okay, they lie close to the kernel, just above the kernel, just below the kernel rather. And their job is to do whatever needs to be done to handle the interrupts. We will see interrupt handler in the software part. You can see this video over there in the playlist. There are two types of interrupts, the precise and imprecise. The precise, the name suggests, is always a welcome option. That means they are sequentially executed by PC. Okay. CPU is doing it, it's done 100%. This one in progress. This one not yet done at all. This few not yet done at all at the moment. So the point is, you can actually, you see what I mean. Not executed, not executed, not executed, not executed, but these are fully executed. And PC is right in here, they're doing the execution for this one. So PC is saved in a known place. All instructions before the one pointed to by the PC have been fully executed. No instruction beyond the one pointed to by the PC has been executed or has been started. Execution state of the instruction pointed to by the PC is known. There's no prohibition on instructions beyond the one pointed to by the PC from starting. But everything must be completed. Okay? Is everything completed before you go to the next part? Imprecise, on the other hand, is where, as you can see, you start servicing multiple instructions at the same point of time at different levels of completion. Yeah. That's okay because the response is faster, but the problem is the machines with imprecise interrupts usually vomit a large amount of internal state onto the stack to give the OS the possibility of figuring out what was going on, because it's difficult for OS to keep track of the PC. So how far and where exactly that will be gone. So that will be a little bit difficult. We move into the software part and see how far we can go. Leaving behind the hardware, when we talk about the software, there are the goals of the software. Okay. As we can see, the programmed I/O, interrupt-driven I/O, and I/O using DMA. These two parts we have already covered. So basically, all we need to cover is the programmed I/O. The goals of I/O software. Again, questions come, which of these are not the goals of I/O software? Something like that. Device independence, uniform naming, a path name is used to address. I can tick some of them. These four are done at a kernel layer of the I/O software, which is called, as you see right here, device independent I/O software. It is, in fact, we'll see it, the kernel module or I/O operation. Okay, device independent I/O software layer. That's one of the most important software layers, by the way. So let's move in and see what is what. Programmed I/O. What is programmed I/O? Programmed I/O is something that we started with before we actually introduced interrupts. And the programmed I/O, we used to write a program. And as you understand, a program is a stable set of, or in other words, a set of logic. I use the word stable because that doesn't change over time. Because once you have written a program, your computer, whenever it executes a program, it will do the same repetitive action, sequential action. So everything will be in the same sequence. That is exactly how we started doing I/O. So we wrote a program And the program will run every time an IO needs to be done. That means every time the CPU switches to the burst mode, the IO burst mode. So CPU is now ready to poll. That the word that we used to use was poll. Okay. CPU will poll somewhere here, right here. The CPU uses polling to watch the control bit. The simplest form of IO is to have the CPU do all the work, as the CPU uses polling to watch the control bit, constantly looping to see whether the device is ready or not. Ready means that whether there's something pending in its buffer. Making a system call to open the device. If it is available, the data will be copied to kernel. Then CPU polls the device to see if it is ready to accept or not. If it's so, the small data is outputted and tying up the CPU full time until all the IO is done. Okay. So that is exactly how it was working. The string to be printed, you send a printer, so what will happen? The A, B, C, D, E, F. Okay. Then it should be put into the kernel. That's what it will do. And final output will come out very slowly. A, B, C, D. Slowly it will come out. But that's not exactly the way you want to see the output. Also, there was another problem. If you are using multiple devices, say for example, when it comes to polling and the programmed IO, that this is the control, these are the controllers. This is the mouse controller, this is the mic controller, and this is the keyboard controller. Right? In their buffer, some data are pending. So now CPU starts polling each of them. And as it's mentioned inside the program, probably every time that comes to polling, it will always poll the mouse controller first, the mic controller second, and the keyboard controller last. Even though there's probably nothing there in some of these controllers, but it must poll because that is what is written inside the program. So say, for example, you typed A, B, C, D, and then clicked the mouse 4 times, and then typed EF and clicked it 2 times. Again, you will have to wait. After a considerable time of waiting, you will start getting the output. And you know how your outputs will come out? Your outputs will come out as you expect. Click, 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 click. A, B, C, D, E. But that's not the way you see, that's not the way you want to get your outputs. Why it is so? Because A, B, C, D, these keyboard controllers will be polled only after the mouse controller has been polled. And while the mouse controller was being polled, all the pending mouse clicks will be served. So you will get response for all the mouse clicks first, and then your A, B, C, D, E, F will get printed out, will be outputted. So there we are. So we see that how it can create some kind of complications. So we move on from programmed IO to interrupt-driven IO. That is the one we were talking about. the interrupt-driven I/O is what we eventually do. And what we do with the way to allow CPU to do something else while waiting for device to become ready is to use interrupts. The CPU doesn't hold the control bit, it simply receives an interrupt when the device is ready for the next. We already talked about interrupts and how interrupts happen, the precise and imprecise interrupts. And in the again back in our uh, so the point is that when we the DMA controller where the I/O will be using the interrupts. We will talk about interrupts once more later when we go to talk about the software part. In fact, the interrupt handler. After this one, we will talk about the software, and there we will have to discuss the interrupt handlers. An interrupt handler is the one that facilitates these interrupts, how interrupts need to be processed. Let the DMA controller fetch the characters to device one at a time without the CPU being bothered. That is what we do in the DMA. The DMA is programmed for I/O. It frees up the CPU during the I/O to do other works, and it reduces the number of interrupts. So these are main utilities because of which we use DMA. We already understand that it reduces the number of interrupts. That's the most important thing. Frees up the CPU. And we need a DMA controller to control this action. Software layers, another important thing, because whenever they ask you the questions about the software layers, don't forget to check the sequence. Don't forget to check the sequence, the hardware, the interrupt, device drivers, device independent operating system software, and user level I/O software. Okay, so we have the user level I/O software and device independent operating system software, device drivers, and interrupt handlers. So you see just the top of the hardware, there's the interrupt handler. So the question that I want to ask from here is, looking at the picture, can anyone tell me where exactly is the boundary for the OS? Is it here? Is it here? Is it here? Or is it here? I mean, where exactly is the end point of the OS? Which part, in other words, these are all software, right? Interrupt handlers, a bunch of codes. Device drivers, bunch of codes. These are definitely codes as well. These are software. So which part, actually, which of these parts belong to the OS and which of these parts don't belong to the OS? The answer is that interrupt handler is definitely not part of OS. It's an independent code, but it is sitting right on top of the OS. So actually the boundary is right here. Remember what I said earlier, that when you install the device drivers are coming from a third-party hardware vendor, not from the OS provider. Microsoft doesn't give you the driver for HP. Okay, so it comes from HP. But once installed, they must sync into the kernel part and make a layer of code. And in fact, this is controlled by the device-independent operating system software. Okay. Traditionally, this should be the boundary. This is the kernel module, and this is the user mode. But after installation of the device driver, these three layers work together as if they are the operating systems. So drivers start behaving in that way. But one thing, you must remember the sequence, the way they have been arranged. If you say device driver first, interrupt handler next, then it's incorrect. You'll get a 0 for that. What is interrupt handler? As I said, a procedure or routine located at a fixed address memory. Okay. And this fixed address is usually on top of the kernel. So the procedure or a bunch of codes does whatever it has to in order to handle interrupt. Does whatever it has to handle the interrupt. It determines the cause of interrupt and performs the necessary processing. It executes a return from interrupt instruction to return the CPU to the execution state prior to the interrupt. It does whatever it has to in order to handle interrupt, determines the cause of interrupt, and performs the necessary processing. Executes a return from the interrupt instruction to return the CPU to the execution state prior to the interrupt. Return from the interrupt instruction to return to the CPU to the execution state prior to the interrupt. So that is what it does. It does whatever. Basically, what it does is think about it. This is the RAM, and this part is the OS. And just on top of the OS, this is a layer of code of the procedure that is called interrupt handler. So when an interrupt happens, it will come straight to the interrupt handler, and the interrupt handler, because they're always running in a dedicated place in memory, so they will immediately do something to free up CPU. And who can free up CPU? Only kernel. So kernel, when interrupt happens, kernel also has a responsibility. As we mentioned in the case of soft timers, you remember, it will immediately have to switch back to the OS will have to switch back to the kernel mode, because that's how it can free up the CPU. And once the CPU is freed up, then CPU can pay attention to handle the interrupts one by one. And once the interrupts, once all the data transfers have been finished, then some other codes inside the interrupt handler will kick in to set CPU back to its old job. So that is exactly how the interrupt handler codes work. The device drivers, the second layer, is a device-specific code. It comes from the device manufacturer and is normally positioned below the rest of the OS. Okay, so that's why there are some restrictions, as you can see at the bottom, are not allowed to make system calls, but they often need to interact with the rest of the kernel. The calls to certain kernel procedures are permitted. There's no technical restrictions on having one device driver control multiple unrelated devices. It's written by outsiders that will be installed in OS. They work as an interface between, as we said earlier, the operating system and the controller. The user process, the user programs. So we have an user space and a kernel space and user space. And in between them, the rest of the operating system is right in here. So we have the printer driver, we have the camcorder driver, we have the CD-ROM driver, and then the printer controller and the camcorder controller and CD-ROM controller. So we have the controllers. Controllers are hardware. Controllers are an intermediary between the OS, and in fact, you can say this is the entire thing is the OS, as you can see. Okay, this picture is very important because you can see the kernel space actually covers the drivers as well. but all the drivers are coming from third-party hardware vendor. Okay. And the independent I/O software is right here. User level I/O software is here. So let's take a quick look at that. Device independent I/O software. The basic functions of the device independent software is to perform the I/O functions that are common to all devices to provide a uniform interface to the user level software. Uniform interfacing, very, very important from the exam point of view. The functions, which remember the names, buffering, error reporting, allocating, releasing dedicated devices, providing a device-independent block size. Each device driver has different interfaces to the OS. Now, driver functions available for system to call differ from driver to driver. There are different kernel functions. Taken together, interfacing each new driver requires a lot of new programming effort. But now these differences are hidden by device drivers. They kind of put up an uniform interface. All drivers now have the same interface. It is much easier to plug in a new driver, providing it conforms to the driver interface. So the driver writers know what is expected of them. So this common interface is created and implemented by this I/O software layer. This is what we talk about. The operating system, SATA disk driver, IDE disk driver, SC disk driver, they're all disks. Okay. With your Windows operating system, you can use any kind of disks. But depending on the disks, the driver will be different. So if you have a uniform interface, then that will be great. In practice, not all devices are absolutely identical, but usually there are only a small device types, and even these are generally almost the same. The buffering in user space, the next one. Buffering is another thing, and they have given an example of modem, which is related to streams. Stream of data input. Okay. So that's how these things keep coming. So a user process provides an in-character buffer in each space. Now the point is, how do you buffer them? Now why buffering is important? Because I think you know about modem, right? We don't use modem these days because we have what I call fiber optics cable for digital data transfer. But in our times, modem was quite popular. Was in fact synonymous with internet. If you think about having internet connection, you must talk about modem. Okay, how to get the modem? Who will give you the modem? The modem's job was to convert digital signals into analog signals and analog signals into digital signals. That's what, because we were using the telephone lines in those days. Using the telephone lines. The telephone lines, the copper lines, copper wires, they were not designed to transfer digital data. So naturally, we had no choice. Okay, I think we will stop right here. No need to rush. In the next class, we will start from the buffering of the I/O software layer. Okay. And then we will finish it and move into deadlock. So I expect that for your presentation, we might actually get started from Wednesday, next week. So stay prepared. Wednesday next week, most likely. Let me take your attendance first, otherwise it will expire. This board. When we take your attendance, Swan Wong, Chi Kang,
Yes.
Vin Phuc, Duc Wong,
Yes.
Luong Ha,
Yes.
Hu Huang,
Yes.
Tan Hung,
Yes.
Nat Phat,
Yes.
Din Min,
Yes.
Quoc Huy,
Yes.
Yan,
Yes.
Kim Tak,
Yes.
Nhật Min,
Yes.
Hiền Phúc, Quang Huy,
Yes.
Minh Quang,
Yes.
Duy Bao,
Yes.
Quay Min,
Yes.
Liêm Trúc,
Yes.
Quoc Hung,
Yes.
All right, start your preparations, and in the next class, we will start from the buffer. We are almost there. And after finishing this part, we will move to deadlock. So uh, we will be needing the next class and also Tuesday, Monday, next Monday. So we will get started from Tuesday for sure. So stay prepared with your presentation. Nothing much left about some of the responsibilities that we deal with. And then we'll go to study deadlock. All right. So that's all. And we will catch up again on Friday. Friday, we will wrap it up and move into the next chapter, deadlock. There in deadlock, you have very basic things, but one good algorithm, an important algorithm. That is. Okay. So that's all for now. And see you on Wednesday. So on Friday. Bye. Goodbye.